In this screencast, we will look at numerical summaries, ways of easily summarizing one quantitative variable. So for starters, let's look at these three histograms. So this histogram is the height of 5,000 randomly chosen women in the United States. And we can see that their heights vary between 55 inches and 70 inches, with a few large, taller or shorter than that. Now this is 500 randomly chosen numbers between 55 and 70. They vary in the same range, but the two histograms look very different. The shapes are different. And then this is our histogram of home prices in Madison, and this is very different. Much different range, much different shape. So in considering quantitative data, we're interested in three things. The location of the data, so where is it? Are we talking about numbers in the hundreds, in the thousands, in the millions? The shape of it, is it sort of flat like this one, more or less? Is it all lopsided like this one, or is it sort of symmetric on both sides like this one? So the shape, and then the spread. How spread out is it? Are all the numbers really close together, or are they far out? And we can summarize data numerically with a handful of numbers. So we'll be looking at the mean, the median, the standard deviation, the 5-number summary, and the interquartile range. Now the mean, it's a measure of the center of where the data is, and it's what we usually think of as the average. In statistics, when we want to be careful, we talk about the mean. It's defined to be, well, what do you think of the average as? You add up all the numbers and divide by how many there are in the sample, or how many numbers you have. And that's just what this says in math talk. This is the Greek letter sigma, and it means add. Xi, that means add all your data points. And that's the number in your data set. So add up all the numbers, divide by however many there are. When we're talking about the mean of a sample, we use X with a bar on top to denote it, just to be a symbol for it. When we're talking about a sample from a large population. When we talk about the mean of a whole large population, we use the Greek letter mu. So in statistics, we use the word mean, but it's what you're used to thinking of as the average. Now, the reason we don't use average for the mean is because there's another number that deserves to be called this, which is a measure of the center, and it has as much right to the word average as the mean does. It's the halfway point. Half the numbers are above it and half below it. It's the 50 percentile. So if your numbers were 1, 7, 13, 19, and 99, the median would be 13. Half the numbers are below 13, half the numbers are above. And there's not usually a symbol for the median, although I have seen capital M or MD for it, but mostly just refer to it as the median. So which is better, the mean or the median? Well, for skewed data, a very few large or very few small numbers, the mean is a little misleading. Imagine a room full of college professors hosting Bill Gates at a luncheon. Then the average income of people in that room would be, hundreds of millions of dollars, but it wouldn't be a very good indicator of either the college professors or Bill Gates. Whereas the median, you couldn't tell really whether Bill Gates was in the room or not, as long as you had, 20 or 30 college professors. So for very skewed data, the median is usually a better idea of the average. It's resistant to outliers, to a few small or a few really, really large numbers. Another thing we want to measure is how spread out the data is. So how far around the mean are the numbers spread? And approximately, it's the average amount by which the numbers differ from the mean. So we have a mean. All the numbers, not all the numbers are exactly the mean, of course. Some are larger, some are smaller. The right way to think about it, it's not mathematically quite correct, but the right way to think about it is the approximate amount by which the numbers on average differ from the mean. And the symbols we use are S for a sample and the Greek letter sigma for a population. And the formula is given by this lovely thing, which is pretty ugly. What does it say? It says take each data point, xi, subtract off the mean, square that, add them up, and divide by n minus 1, and then take the square root. So let's just look at an example before we talk about that. Let's find the mean and standard deviation of these 6 numbers. 1, 3, 4, 5, 5, 6. We'll see that the mean is 4 and the standard deviation is 1.79. So the mean, you add the numbers up. 1 plus 3 plus 4 plus 5 plus 5 plus 6. Divide that by 6, and you get 24. Sorry, and you get 4. So the mean, the average is 4. Not real surprising. And then to find the standard deviation, for each number in the data set, starting with 1, you subtract the mean 4, square it, add those up, and divide not by 6, but by 5. Why? Technical reasons we're not going to go into. You do all that, and then you take the square root, and you get 1.79. And again, the right way to think about it is that on average, these numbers are about 1.79 away from 4. Some are further away, some are closer. So what does the standard deviation really tell us? Let's try to figure that out. If you take a first job out of college at a company with a mean salary of $75,000, would you hope that the standard deviation of the set of all the salaries is large or small? Well, this is your first job out of college. You're going to be starting at the low end of their scale. So you want their low end to be as close to 75,000 as possible. So when you say the standard deviation is small, that means that the numbers are more or less close to $75,000. If it's large, they're spread way out around it. Well, if you're going to be at the low end, then you hope they're close, so you hope the standard deviation is small. On the other hand, a student is told that the average amount spent on textbooks at her school is $1,200, but that students in her major spend at the lower end. Should she hope that the standard deviation of spending on textbooks is large or small? Well, if she's going to be at the low end because of her major, she wants that low end to be as far from 1,200 as possible. So now she should hope that the standard deviation is large. So if you can understand questions like that, you start to begin to understand standard deviation. Small standard deviation, the numbers are relatively close to the mean. Large standard deviation, the numbers are relatively far away from the mean or spread out around the mean. Another measure of spread is what's called the interquartile range. So the median is the 50 percentile. Half the data is below and half is above. It's also called the Q2, the second quartile. Q1, the first quartile, 25% of the data is below. Q3 is the third quartile, 75% of the data is below. And the interquartile range is Q3 minus Q1. It's telling you that it's telling you that 50% of the data is in a range that wide. And then the 5-number summary is the smallest number in the data set, the Q1, the Q2, the Q3, and the max. And loosely speaking, a box plot is just a picture of this 5-number summary, except for outliers. Again, with very skewed data, the IQR, the interquartile range, is usually a better measure. So here's an example, the homes for sale in Madison. The means at the time I created this, or at the time we had this data set, it's gone up since then, was 260,895. The median, about 210,000. Standard deviation, 184. Interquartile range, 110. 5-number summary. So the cheapest home at that time was a little under 50,000. The most expensive was 2,600,000. So notice here that the mean is quite a bit larger than the median. So they're both averages. They're both trying to tell you what's going on, but the mean is much larger. Why? Because the data is skewed. We have some very large numbers going all the way up to 2,600,000, and they just pull the mean up. And that's why the median is a better idea of what happens on average. And again, a little warning, this data is several years old by now, so this is not current, but for that particular data set, this is what we had. Oops. And a reminder of how to do this in Excel, and that's it.